It's 3 a.m. at an oil refinery. A massive power transformer just tripped, and the entire production line grinds to a halt. Every minute offline burns tens of thousands of dollars. On an older, hardwired relay panel, getting the system back online is a grueling ordeal. 2 technicians face 4 to 6 hours of meticulously disconnecting and rewiring test leads in the dark. But with a modern modular panel, a single technician can slide out the old unit and slide in a spare, a 15-minute job. That rapid recovery is built into the hardware of the ABB RET615. This protection and control relay is engineered specifically to make these ultra-fast module swaps a standard operational reality. The relay's core objective is to continuously monitor the currents and voltages flowing through the transformer. If it detects an abnormality, it immediately commands a circuit breaker to trip and isolate the fault. There is a constant tension between the speed of a fault and the speed of maintenance. Transformers fail in milliseconds, yet traditional maintenance on the relays protecting them often requires hours of vulnerable system downtime. Maintenance delays create a critical electrical vulnerability. If protection is offline for hours during a relay swap, the transformer remains exposed to the very faults the relay was installed to prevent. Solving this vulnerability requires a rethink of the relay's mechanical design. Think of the RET615 like a hot swappable hard drive in a server rack. You replace the failing component without shutting down the entire system. Disconnecting a live current transformer under load creates an open secondary circuit, generating a massive, lethal voltage spike that destroys insulation. The RET615 eliminates this risk by automatically engaging internal shorting mechanisms as the chassis is withdrawn. Because the external wiring is attached to a stationary terminal block behind the unit, the technician never touches a live wire. Only the relay drawer moves. The connections stay fixed. This mechanical foundation is a primary safety feature. It eliminates human error during a high-pressure outage and ensures the facility's protection stays online more of the time. This flexibility extends to how the relay reads electrical signals. Standard current transformers in a switchyard output signals at either a 1 amp or 5 amp level. The RET615 includes a software setting to toggle between these 2 inputs. This allows the same physical relay hardware to be deployed across different substations, regardless of the existing CT ratings in the yard. For a plant manager, this logistical standardization reduces procurement delays and minimizes the need to stock multiple hardware variants for different areas of the grid. While module swaps save hours of maintenance time, certain events require saving milliseconds. An internal arc flash inside a switchgear cabinet is a near instantaneous release of violent thermal energy. This graph shows why current-based protection is often too slow for an arc flash. A traditional overcurrent algorithm must wait multiple cycles for the current waveform to peak, but an arc produces an unmistakable burst of light, detected in a fraction of a cycle. The RET615 monitors this light through 3 independent channels, watching the circuit breaker, the bus bar, and the cable compartment simultaneously. Identifying the specific compartment where the flash occurred allows the relay to use targeted isolation logic. It trips only what is necessary, rather than shutting down the entire lineup. Bypassing current measurements in favor of light detection isolates these faults up to 20 times faster, preventing catastrophic tank ruptures and saving the transformer core from permanent damage. There is one final vulnerability: the relay itself. If the protection hardware develops a silent internal fault, it might fail to trip during a real event. To prevent this, the RET615 runs a continuous diagnostic heartbeat. This self-supervision system flags internal hardware or software failures the instant they occur, alerting the operator before the fault matters. This approach masters 3 distinct timescales: clearing arc flashes in milliseconds, completing physical hot swaps in minutes, and maintaining a continuous second-by-second watch over its own internal health. Modern power protection requires minimizing exposure at every conceivable window. By shrinking these intervals of risk, the industry ensures its most critical assets stay online and its personnel remain safe.